Every star is locked in a cosmic tug-of-war. For billions of years, a dying star fights a desperate battle against its own mass, as gravity endlessly attempts to crush its matter down into an increasingly smaller space. The star pushes back. The outward pressure of nuclear fusion, and later the sheer repulsive force of quantum mechanics, temporarily halt this collapse, compressing the remaining matter into an ultra-dense core like a white dwarf. But this quantum resistance has an absolute limit. At only 19 years old, physicist Subramanian Chandrasekhar proved that if a star's mass is large enough, the gravitational crush will completely overwhelm those outward quantum pressures. When the core collapses past this threshold, the surface gravity becomes so immense that not even light can escape its pull. An event horizon forms. The formation of that horizon marks gravity's absolute victory over matter, and it triggers a severe crisis for our understanding of physics. Beneath that dark horizon, the collapse is supposed to continue forever, until the star's matter is crushed into a singularity, a point of infinite density. In the 1970s, Stephen Hawking discovered a complication. Black holes are not permanent fixtures of the universe. They slowly leak energy, Hawking radiation, and over immense stretches of time, they shrink into nothingness. This flowchart illustrates the resulting paradox. As complex matter crosses the event horizon, it is dragged into the singularity. When the black hole eventually evaporates into an empty void, it takes the structural data of that matter with it, completely deleting it from the universe. This deletion creates a direct conflict between our two most reliable frameworks of nature. Quantum mechanics dictates that information can never be destroyed. General relativity predicts a singularity that destroys everything. They cannot both be true. If singularities exist and destroy information, our foundational laws are flawed. To preserve the rules of physics, the universe must possess a hidden mechanism to prevent that infinite collapse. To find that mechanism, we have to plunge past the event horizon and follow the collapsing star as it races toward the theoretical singularity. Physicists like Carlo Rovelli propose a solution through a framework called loop quantum gravity. This theory redefines space itself, modeling it not as a smooth, continuous fabric, but as interwoven, blocky, three-dimensional threads. In this model, space has a minimum, indivisible scale, known as the Planck length. You simply cannot divide geometry into anything smaller. As the dying star is crushed down to this microscopic scale, it hits this rigid, quantized minimum floor. The grainy structure of spacetime pushes back with immense quantum pressure, forming a Planck star. Instantly, it violently rebounds outward, triggering a reverse Big Bang. By introducing a geometric limit to space, loop quantum gravity replaces the impossible math of a singularity with an instantaneous outward explosion, a white hole. If every collapsing star instantly bounces back outward as a massive white hole, why isn't the night sky constantly flashing with blinding explosions? The answer lies just above the surface of the Planck star, in the extreme effects of relativistic time dilation beneath the event horizon. The immense gravitational field creates a severe time mismatch. For an observer in the outside universe, millions of years pass, but deep inside, relative to that same observer, time grinds to an absolute halt. The outward explosion of the Planck star takes only a fraction of a second locally, but from our perspective on Earth, that microscopic fraction of a second is stretched out over billions of years. A black hole is exactly that, a blindingly fast, universe-ending explosion that gravity has suspended and frozen in time. Fast forward billions of years into the distant future. The frozen black hole slowly leaks away its mass through Hawking radiation, steadily shrinking in size. Eventually, the contracting event horizon reaches that exact same quantized floor of spacetime. Its evaporation halts permanently at the microscopic Planck scale. This creates a massive spatial paradox. The frozen Planck star trapped inside this event horizon is actually trillions of times larger than the microscopic border containing it. This diagram visualizes how extreme internal gravity severely warps the local geometry. It allows a tiny exterior shell to cleanly encapsulate a massive internal pocket of space. The final state of a black hole is a microscopic Planck relic, a tiny speck that safely locks away a vast volume of energy. At this absolute final stage, the black hole is entirely microscopic, meaning it is now governed by the chaotic, unpredictable laws of quantum mechanics. At the quantum scale, systems can spontaneously tunnel between different states. The relic begins to transition back and forth between being a collapsing black hole and an exploding white hole. This continuous transition locks the relic in a quantum superposition. It exists in both states, flickering endlessly between pulling matter inward and pushing energy outward. Because the star bounced instead of infinitely collapsing, the singularity never formed. All the original quantum data of the dead star, everything it ever swallowed, remains perfectly preserved inside this flickering pocket. The universe does not rely on broken physics to resolve a dying star. It simply contains the violence of a Big Bang in an eternal microscopic quantum stasis, protecting its own laws and ensuring that no information is ever truly lost.